इसको इधर से अनम्यूट करना पड़ेगा। इधर से तो है सॉरी हेलो हेलो अच्छा कौन से ये इसको म्यूट कर दो इसमें हाँ
So we study acyclic directed graphical model where we have a DAG and that represents a set of conditional independence relations. For example, this is a DAG and each xi is independent of its ancestor given its parents. For example, x5 is independent of x1 and x2 when we have given x3 and x4. A probability distribution P always this DAG if the distribution of probability, if the probability of x1 to xn or the random variables is equal to product of pxi given its parent. In the directed acyclic graphical model, each edge, say x1 to x3, so here x1 is couch and x3 is its direct effect. For example, in this one, C is independent of A given B. And a distribution, if P is always this there, then probability of ABC, probability of A given into probability of B given A into probability of C given B. Here A to B implies A is the couch and B is direct effect. So there can be more than two DAGs, more than one DAG which represent the same conditional independence relation. We call them Markov equivalent. Verma and Pearl give a necessary and sufficient condition for two DAGs to be Markov equivalent. They say that two DAGs are Markov equivalent if and only if both have the same skeleton and same set of base structure. Skeleton means underlying undirected. Skeleton means underlying undirected graph. So here this is the skeleton of these two DAGs, and both have the same base structure. So base structure is this structure. ACB type of structure is called the base structure. So both have the same base structure and same skeleton. So these two are Markov equivalent. So is there any other DAG other than D1 and D2 which is equivalent to D1? So any equivalent DAG, any Markov equivalent DAG which is equivalent to D1 must have this base structure. So the uncertainty is only on this edge.
So I didn't make my both D1 D2 have the same base structure.
So both have this. So this is the base structure, ACB type of structure.
Okay. So B is directed inwards, not outwards. Oh,
okay. So both have the same base structure. That's why they are Markov equivalent. Both have the same skeleton also. A Markov equivalence class is set of Markov equivalent DAGs. So and we can represent graphically a Markov equivalence class by taking union of all the DAGs it contains. So for example, if we take the union of these two DAGs, then since both of the this directed edge, so even in the union we will get directed edge here basically. And since D1 has edge B to D and D2 has edge D to B, the union have an undirected edge BD, which says that there are some DAG which has edge B to D and there are some DAG which has edge D to B. So this one. So this is undirected and this is undirected. So we can see the set of base structure contained by the MSC and its DAGs is same. We come up with a set of where we have, if we have given a set of conditional independence relation, then we can construct the MSC that contains all the DAGs that represent the conditional independence relation given. Anderson give a necessary and sufficient condition for a graph to be an MSC. So he said that if a graph G is an MSE, then it must have, it doesn't have any directed cycle. All the directed connected components must be coded. There can't be any induced graph of this form, and all the directed edges must be in one of these form. So if we have given us MSE, then size of an MSE says the uncertainty of the causal model it contains. Because if we have given an observational data, there can be many sets that represent the same set of condition independent relation that contained by that observational data. For example, if we have this MSE, we have given an input MSE. So this is a combinatorial problem that we have given a graphical representation of an MSE, and we have to answer a number of decks that contain that. For example, this is an MSE. There are three decks. That contain by this one. So we can see that all these three decks have the same skeleton as this one, and since these have no base structure, none of them has any base structure. In many cases, we get some extra information about the direction of edges other than what is given in the MSE. We call them as background knowledge. We get this background knowledge through some prior knowledge or through experiment or interventional knowledge. For example, intuitively, we can say that what if in an MSE, there's an undirected edge between medicine and cure, then we can intuitively say that which one is cause and which one is effect. So this brings another combinatorial problem where we have given a graphical representation of an MSE G, and we have also given some set of directed edges, and we have to answer number of decks of this G which are consistent with K. For example, this is an MSE, and suppose we have given, and this is the background knowledge we have. So these are the two decks which are, so earlier we have seen that there are three decks inside this MSE. So now only two decks which are consistent with C2A. Both have C2A. So there are recently many works done on this problem. So finally, Wienöbst come up with a polynomial-time algorithm that counts decks of an MSE when there is no background knowledge given. He also saw that the counting background knowledge consistent decks problem is number PR. So it is number. So the counting background knowledge consistent decks. This problem is number PR. So we come up with a fixed parameter tractable algorithm that solves this problem. So fixed parameter tractable algorithm has in the time complexity two parts. One is so there are two terms. One is input size, another one is the parameter K, and the runtime is polynomial in terms of the size of the input, and F key can be exponential. Normally, this approach is used when we want to solve computationally hard problems. So our parameter is click knowledge. So click knowledge is for a given MSE and background knowledge for any click. So this MSE, this AB is a click. So click knowledge of this AB is the number of nodes of this click that are part of an edge in the background knowledge with both endpoints in this click. So both AB are part of this edge A to B. So this click has click knowledge too. And this one, EDF, this has click knowledge also too, because only E and D are part of a directed edge, part of that edge in the background knowledge. F is not part of any edge in the background knowledge. But in this case, the clique knowledge of this clique is not 3 because F is also part of LH, which has both ends point in this clique here. So max clique knowledge is the maximum clique knowledge among all the cliques we have. For example, in this case, we have the max clique knowledge is 3, and in this case, max clique knowledge is 2. We come up with algorithm. We give up APT algorithm that runs on factorial k square and to the power 4 times and counts background knowledge considered DAX of an MSC, where k is the max clique knowledge of the background knowledge. Our experimental analysis validates our claim. So we know theoretically, we give the theoretical proof of this. So acyclic model orientation is that which has for a graph, and acyclic model orientation is that which has both same skeleton and same set of B structure. So we can see that if G is an MEC, then each DAG of that MEC is an acyclic model orientation of that graph G, and each acyclic model orientation of the graph G belongs to that MEC. So now, the problem is convert from the set of counting k consistent DAGs of an MEC to counting k consistent acyclic model orientation of a graph. We found that each acyclic model orientation of a graph G is union of two parts. One is directed subgraph, and another part is the union of all the union of acyclic model orientation of its undirected connected components. So this is an AMO of G, and this is union of this directed subgraph of G and undirected acyclic model orientation of the undirected connected components of G. So this reduces to the this reduces the problem from counting to counting acyclic model orientation of a chordal graph, since from the Anderson results each undirected connected components is chordal graph. So each acyclic model orientation, there is a ordering of the vertices which can represent the DAG. So for this DAG, ABDC represents the if for any edge directed U to B, tau is less than tau means the ordering the initial node of the edge comes before the final node. So ABDC represents D, but ABCD then because there is edge D to C, so D must come before C, and here it is now. An LBFS ordering of so our approach is, so we actually map each acyclic model orientation with a maximal key. For this, we need the LBFS ordering. So an LBFS ordering of a chordal graph. Remember, the graph we have is a chordal graph. So LBFS ordering of a chordal graph starts with a maximal key, and the parents of each node forms a clique. So this is an example of LBFS ordering, and this is the corresponding acyclic model orientation that is represented by this. So remember, there is 1, 2, so the direction of edge is 1 to 2, similar for all the other edges. So what we did, we map each acyclic model orientation of an undirected connected chordal graph with a unique maximal clique C alpha. Okay. We call this C alpha as a canonical representation of alpha. So this reduces problem from counting acyclic model orientation of a graph G into counting acyclic model orientation of graph G, those acyclic model orientation of graph G which is represented by click C alpha. For this, we take the union of all the acyclic model orientation of G that is represented by the maximum click C, and this gives us a recursive relation, and this reduces our actual problem into smaller undirected connected components. So for counting acyclic model orientation of background concerning acyclic model orientation now becomes counting permutations of this click and counting acyclic model orientation of the undirected connected component of BC. Where this is the union of all the AMOs of G that is represented by backslash clicks. So this counting k-concept permutation of C reduces to this, that we have to count number of permutation of a click which are k consistent, and here we need our parameter max click knowledge, and this will take order factorial k times k squared. Continues the proof. So the open problems are, can we do some another? We can have another error which is beta time complexity, or can we have some another parameter?
Any questions?
Markov equivalence class consists of one graphs which have the same skeleton and the same B structure. The skeleton part I understand what is the class.
B structure is an inductive graph of the form A to be directed and C to be directed.
Why is that? Why only that take
This comes from the that Verma and Pearl result that.
But why, like, I mean, can you give a simple example of B structures really are?
So. First one.
Yes.
For example, take a graph which has a B structure, say A to C and B to C. So if we know that A is in this time, the conditional dependent A is not independent of B given C.
Yes.
But in this case, here see this one. Now in this case, A is independent of C given B.
B.
A is independent of B given C.
Okay.
Okay, so
This kind of structure that the edges are going out.
no, B structure is just for income.
So when you in that what is the risk? It's like A and B are still conditionally independent given.
Is
A and B are still conditionally independent given. In that
no. In this case, yes, A is still A is independent of B given C.
Okay, let's